and false things over here to impossible things over here, our paraphrase function has to at least preserve truth value. So if you send something true to something false, then things have gone wrong. What I'm assuming is that this feature, the preservation of truth value, not depend on the assumption that the world is infinite. And the reason I'm assuming that is because, remember, the idea is that if you have a truth of pure mathematics, that's supposed to be mapped onto something which is trivially true. So there is nothing special God had to do or refrain from doing in order to make it the case that that holds. So in particular, it is not the case that God had to make sure that the world is infinite in order for it to be true. It's the kind of thing, it's like a tautology. It's the kind of thing that imposes no requirements on the world in order to be true. Now, there is a certain kind of crazy view. In fact, I hold this crazy view, but I admit that it's a crazy view, according to which even assuming that that when you say that there are infinitely many things, you say nothing of the world because a finite world would be absurd. Okay, so if you think that, then God must have created a world with infinitely many things. There's like no non-absurd way of doing it. But that is a very controversial assumption. In order to keep the nominalist paraphrase function uncontroversial, we need to assume that this preservation of truth value is going to work, even if this world is finite. So that's assumption 2. And I'm not going to say much about assumption 3 unless people want to ask. But the main thing is that I'm going to request that it include no modal operators. And there are reasons for that. If you don't know what a modal operator is, then don't worry. It won't matter. So as a first approximation, think about the 2 constraints as you don't allow for languages of infinite order, and you don't assume that the world is infinite. Those are the main assumptions. So going on to page 4, if you look at number 5, you can now see the result. So what the result says is that there is no paraphrase function for the language of arithmetic that can satisfy the following 3 assumptions. The output language is an nth order language for a finite n. The output language contains no modal operators, that's the thing I skipped. And preservation of truth value does not presuppose an infinite domain. The proof is super easy. In fact, the proof is on the margin, if anyone wants to look at it. And it is to do with Gödel's theorem, though it's to do with the other Gödel's theorem. But it just can't be done. So let me sum up. What I did was describe nominalism, and then see what happens when you don't just say mathematical talk is a façon de parler, but instead rigorously specify what it is you're really saying about the world. And proved that on certain reasonable assumptions, there is no way of spelling out the façon de parler. So there is a very real sense in which the nominalist dream needs to be reconsidered. So that's part 1.
Okay, thank you.
Well, I feel like I should be merciful.
Yeah, and we can maybe have some questions about it.
Oh, yes, absolutely.
And with plenty of time for questions, I would give priority to students and then PhD students. Right.
PhD students?
No. Students.
Okay.
Overall.
Well, I understood what you did. The proof you mentioned at the end of your relation, at the end of your talk. I want to ask you if there are similar results in the field of geometry, Euclidean geometry. If the nominalist dream has serious problem, or also in defining a preference function for Euclidean geometry as well.
I'm annoyed at myself because I feel like I should be sure about the answer to this question, and I'm not sure. I'm gonna have to conjecture. So I'm almost sure that what I'm about to say is correct, but it may be incorrect. Okay. The theorem holds for elementary arithmetic. So it holds for a super, super simple theory. The result of that is that it will also hold for any theory in which basic arithmetic can be interpreted. There are many theories in which it is known that arithmetic can be interpreted. So for example, that's true of analysis. It's certainly true of set theory. So the result immediately carries over to analysis and to set theory. Now, the thing I now can't remember is what exactly you need to assume regarding geometry in order for arithmetic to be interpretable within geometry. I'm sure that if you make certain assumptions, it can be done, because you can just like have a line which you treat as the unit length, and then you have axioms governing like what it is to add a unit length, and you can easily define multiplication. And so, like with the right postulates, you can interpret arithmetic in geometry, and then the theorem will apply. But I just can't remember what you need to add. What I can't remember is whether it's just definitions or whether you need to add some extra axiom in order for it to be the case.
Okay, thanks.
But look, your point is important because the result would be much less interesting if it turned out to be an exception. So, like if it turned out that, like, for most mathematics, you can produce a nominalist paraphrase function, but it just like so happens that I found like one little bit for which it can't happen. But in fact, it's the other way around. Because arithmetic is so basic, what that means is that basically none of mathematics can be paraphrased.
Are you sure that your triviality constraint is a consequence of every possible nominalistic proposal?
No.
Okay.
That is a very nice point. I think that whereas my first two constraints should be completely uncontroversial and every nominalist should accept them, I do not think the same is true of the third constraint. So I think that the best way of thinking about the version of nominalism that accepts all three is as ideal nominalism. So I think that, strictly speaking, what the result shows is that you can't get the ideal version. If you drop the trivialist constraint, then there is something very, very cool that you can do. And that was what my PhD thesis looked like in the end. So let me tell you how you can do it. And even though I think that this is deeply imperfect, I still love it. I still think it's incredibly beautiful. Okay. So let me give you a little background. Okay, so I'm going to describe a nominalist paraphrase function, and I'm going to describe one that does not satisfy the final constraint. And in doing so, I'm going to use a second order language. So I'm going to allow that kind of formula. Now, the paraphrase, so the English reading that I suggested for this is so incredibly awkward and hard to understand that in order for what I say to be intelligible, I'm going to read these formulas in a slightly different way. So what I'm going to do is, instead of saying that, I'm going to say this. Think of these as plural variables. So just like when you say this, so I'm going to put it like that. So you can read this as saying, there is something such that that thing is Susan's father. So there is a thing such that it is Susan's father. You're going to read this as a plural version of this. So you're going to read this as saying, not there is a thing, but there are some things such that, and I'm going to read this as Susan is one of them. So we have an ordinary quantifier, and we have a plural quantifier. Now, a cool thing that you can prove is that under certain assumptions, this plural language is just as powerful as a second order language. And the plural language has the advantage that it's easy to understand, and it's easy to pronounce. And so what happens in practice is that really, whenever people should be talking about second order languages, they just talk about plural languages. And in order for what I'm about to say to be intelligible, I'm just going to use a plural language. I got my PhD at MIT, and the reason I went to MIT is because that's where the guy who discovered this connection was. I wanted to be like him in every way. And then I showed up to MIT and discovered that he had died. And it was a terrible thing. Okay. His name was George Booles, by the way. Okay. So what I'm going to describe is the main result in my thesis, and that result is a paraphrase function that maps every arithmetical sentence onto a sentence of a plural language. Okay, here's how to do it. So let's first deal with sentences of this form. The number of the F's equals the number of the G's. So sentences of that kind get transformed into the F's. Are just as many as the G's. In this expression, just as many, let me put this here. one thing that Frege pointed out is that this expression just as many can be spelled out in a second order language. It's just the relation of 1-1 correspondence. So what it means is that you can do a mapping between F's and G's. So like if the F's are the boys and the G's are the girls, you can get each boy to hold the hand of one girl and there's no one left. So this is an English version of a second order sentence. So whenever someone says this, you say, that's just a façon de parler for this. The F's are just as many as the G's. And now, when someone says, there is a number n such that n equals the number of the G's, the way you paraphrase that is by saying, there are some things such that those things are just as many as the G's. And it turns out that using just expressions of that kind, you would express all of arithmetic. So with like boring definitions, that transformation method is enough to paraphrase all of arithmetic. I love it. I'm completely in love with that transformation method. Unfortunately, it has the problem that there are some mathematical truths that get mapped onto sentences which presuppose an infinite world. So it's not going to be the case that every truth of pure arithmetic gets mapped onto something that would have been true regardless of how God had chosen to make the world. Sorry, maybe there was a longer answer than you were hoping for.
Other questions? Yes.
You used before the notional actual word.
Can you speak up?
You used before the notional actual word. Could you give me your formal definition of the actual word? Is it a domain of logic or something more? What do you mean for it?
What I mean by the actual world is this, this thing here. Sometimes modal logicians use that term to distinguish between the way things are and the way things might have been. So the idea is that the actual world corresponds to the way things are, and merely possible worlds correspond to the way things might have been. I sort of took that notation and used it for a slightly different use. So I was merely intending to distinguish between what exists, what really does exist, and what exists according to a certain fiction. The fiction that the nominalist is employing when setting forth assertions as a façon de parler. So think of it this way. It's a little bit as if when I said there are butterflies in my stomach, I was imagining a fictional world in which there really are butterflies in here and those are causing the sensation. And then there are certain rules about how our world, the real world, correlates to that world. So maybe in this case the rule is something like that whenever someone in that world has butterflies in their stomach, someone in this world just has that strange sensation. And that's how you can use fictional worlds to learn things about the real world. So my answer to your question is, by actual, I just meant real. I just meant the way things really are.
So my question is, can we really build such a set? I mean, what's the recursive view to build the set to actual work? Because we have it, I think, for smaller sets.
Oh, so are you thinking that maybe the things that exist are too many to form a set? So if you wanted to use set theory,
in some senses, yes.
There once was a day in which, like, the main thing that worried me in life was that problem. Okay, so let me give a little bit of background. Sorry, this again is going to be maybe a longer answer than you were hoping for, but I can't resist. Okay, so it all starts with Russell's paradox. So the most natural way of thinking about sets is that whenever you have some things, there's a set of those things. So there are the elephants, and therefore you have the set of elephants. And there are the stars, and therefore the set of stars. And there are the sets, and therefore the set of sets. So it's natural to think that whenever phi is well defined, there is a set, which is just the set of phi's. And Frege developed the theory of sets, which was entirely sensible, which entailed this. And then, as some of you may know, he received this horrible letter from Bertrand Russell, which says something like, oh, you know, I read your book and it's wonderful. I myself have been thinking similar things. There's one little issue that I noticed. And the little issue that he noticed is that from that assumption you can derive a contradiction, which meant that like the entire project was undermined. It's like the most horrible thing that can happen to you in your intellectual life. And the reason you can derive a contradiction is because you say, well, look, if whatever phi is, you have a set of phi's. Well, what about this set? I'm going to call it R after Russell. The set of things which are not members of themselves. So is it the case that R is in that set? So in other words, is R a member of R? And you'll say, well, suppose R is a member of R, well then it satisfies this condition. But to satisfy that condition is to not be a member of itself. So if you assume that R is a member of R, you can prove that it's not a member of R. So it can't be a member of itself. But wait, if it's not a member of itself, then it satisfies this condition. And to satisfy that condition is to be a member of R. So if it's not a member of R, it has to be a member of R. So it can be neither in nor out. So you get a contradiction. So this wonderful principle about sets, that whenever you have some things, there's a set of those things, turns out not to be tenable. And basically, we've been trying to recover from that observation ever since. And my sense is that like nobody really has like a good answer about like what to do with set theory, given that we can't understand sets that way. But here is one thing that some people have said. One thing that some people have said is that you have to build your sets with a certain restriction. Whenever you have few things, those things can form a set. But if you have too many things, in particular, if you have as many things as there are things, if you have as many things as the universe has things, then those things don't form a set. So now we can get to your question. So suppose that you think of set theory in this way, then it's very hard to produce a mathematical model that captures talk of absolutely everything. Because as standardly understood, the domain of a model is just a set. But if your model is supposed to capture talk of absolutely everything, then that set would have to contain everything. In other words, it would have to be too big to form a set. So there can be no set. So there can be no such. So, that's a problem. So earlier I told you about chapter 3 of my thesis. Let me now tell you about chapter 2 of my thesis. So my thesis was all about what you can do with second-order languages. So one thing you can do with second-order languages is produce the paraphrase function, which I just described. Another thing you can do is define the notion of a supermodel. So in ordinary models, the domain is a set. In supermodels, you use plural variables to talk about the domain. So instead of saying that there is a set such that you're a member of the domain if you're a member of the set, what you say is that there are some things such that to be, let me call it a domainer, is to be one of those things. And what I showed together with Gabriele Luciano is that it is possible to give a precise definition of a supermodel, and you can use it to do everything you want it to do with regular models and more. So here's a summary. The summary is that you have pointed to a real problem. So if you make certain assumptions, then you think that there are too many things to form a set, which means that you can't use standard resources to talk about the needed models. But if you're happy with second-order languages, then there is a technical trick that allows you to overcome the difficulty. I should say for the record that I have now completely changed my view about these things, and I think about sets in a different way, and I no longer think it makes sense to talk about everything there is. So now I've developed my own crazy other way of dealing with this. But the standard way is the one I earlier described.
Good. Other questions? Yes.
So you mentioned second-order logic. I would like to know what you think of it. I mean, as you previously said, there was a critic by Quine to second-order logic, but I think you have a good, how can I say, repetition of second-order logic. I heard what you said before. So if you can briefly explain what do you think second-order logic is important for us? I mean, important for us, why we should not only learn but adopt it, regardless of what Quine said.
Good. So answering this question will basically be the story of my intellectual life. Because I was very interested in this very question for some time. Okay, so I grew up with Quine. So when I was a little boy, intellectually speaking, I just thought that everything Quine said was true. So when someone wrote down a sentence like this, I genuinely had no idea what that might mean. My best effort to understand it was something like, there is an alpha such that alpha is a set and S is a member of that set. Or I thought even worse, something like there's an alpha such that alpha is a property. And that property is instantiated by S. So I thought, look, if that's what you mean, why are you playing games? Why do you use this like weird notation? Why not just like do things honestly and use a first order notation? And then, you know, it's not pretty, but at least you're honest. Okay, so this was my original view. Then came George Boulos, the great MIT guy who died just before I got there. And one thing he noticed is that it's a mistake to think that these are the only ways of understanding what one means by that. There's this other way, which is, this is a slight simplification, but something like, there are some things such that S is one of them. And then it was like the scales fell from my eyes. And I thought, my God, maybe Quine wasn't right after all, because it was just a mistake to think that these were the only ways of reading this formula. There's another way of reading it, which obviously makes sense. You know, why not just go with that? During those years of excitement, there was another thing that the field got clear about, which is that when it comes to first-order languages, there are all these metatheoretic results, which Francesca has either told you about or will tell you about if you take the second logic class. So you have a completeness theorem that shows that the syntactic relation of entailment corresponds with the semantic one. You have compactness, which shows that if something is a consequence of an infinite set, then it's a consequence of some finite subset. You have Lowenheim-Skolem, which shows that if something has, if a theory has an infinite model, it has an infinite model of any size. And when I was a little boy growing up with Quine, I thought that these were all wonderful results. I thought that all of this was like good news. It meant that first-order languages were like so tractable, so easy to study. I think it was glorious. But after Boulos, what I, reading other people, realized was that in fact, all those results were criticisms of first-order languages because they're just consequences of expressive poverty. I came to see the reason you can prove all those things is that first-order logic is so incredibly weak. So, for example, the reason you can prove compactness is because there is no formula of first-order of a first-order language that says there are finitely many things. That's the only reason you get that result. So it's not good news. It's a mark of the poverty of the language. In a second-order language, you can say things like there are finitely many things and much, much more. So the answer to the first part of your question, what can you do? You can do so many more things. So, for example, as Gödel proved, there is no recursive and complete first-order axiomatization for arithmetic. But there is a second-order version of the standard axioms, which is semantically complete. In other words, any two models of those axioms are isomorphic to each other. Amazing. So you can use a second-order language to truly pin down the structure of the natural numbers. And that's only the beginning. There are all sorts of things you can do. Okay, so those were the glory days. So life is winning. But then came my friend Agustin. So the same year that I started graduate school at MIT, he started graduate school at Harvard. And Harvard and MIT had very different ways of thinking about second-order languages. So my advisor was Van McGee, who was very much of the Boulos way of thinking of things, and also Boulos' spirit continued to live at MIT. But Agustin at Harvard was much more influenced by Charles Parsons. And Charles Parsons had a view which at the time I found unintelligible. Like I didn't know what he meant. He would put it by saying things like, there's no real difference between ontological assent and ideological assent. In other words, if you read this formula this way, one way to think about what you're doing is you're adding extra things to the world sets, and that's what allows you to say more things. If you read it this way, then you're not adding new objects, but you are adding new ways of talking about the old objects. Before you can only talk about them singularly, now you can talk about them plurally. And the view was something like, the difference between this ontological increase and this ideological increase isn't really a deep difference. And I had no idea what that even meant. But Agustin and I went from being philosophical nemeses to really together getting clear about many of these issues. And I have come to adopt the Parsons view. So this is what I now believe. Let me start with an analogy. So here you have two sentences. Socrates' death took place, and Socrates died. So the old Agustin thought that these two sentences said very different things. What their truth demands of the world is very, very different. And let me tell you why. In order to make this sentence true, all God had to do when creating the world is create Socrates and make sure that he dies. But not for the other sentence. For this sentence, God had to do all that and more. Because God also had to open the events drawer. Like, look around until God found a death. Then add the death to the world. And then make Socrates the agent of that death. So put in terms of Quine's notion of ontological commitment, whereas this sentence is only committed to Socrates and to things that die. This sentence is committed to deaths, to events of a certain kind. And I thought those are very different demands on the world. I've since come to think that that's a horrible mistake. I've since come to think that for Socrates' death, for Socrates' death to take place just is for Socrates to die. In other words, when God made the world and made it the case that Socrates died, God was done. There was nothing extra that needed to be done in order for it to be the case that Socrates' death takes place. And similarly, I have come to believe that for the number of the dinosaurs to be 0, just is for the number of the dinosaurs to be 0, just is for there to be no dinosaurs. That is, when God made the world and made it the case that there were no dinosaurs, there is no need to open the special numbers drawer and add the number 0. God was already done. These two are different descriptions of the same feature of the world. And finally, to come back to your question, I've come to believe that, for example, for Caesar to be a member of the set of Romans just is for Caesar to be a Roman. And more generally, that for it to be the case that there is a set such than so and so, just is for there to be some things such that something corresponding to so and so. So for there to be a set of Romans, just is for there to be some Romans or none. In other words, I've come to take the Parsons view that there is no deep difference between ontological assent and ideological assent.
Can I cut your answer to leave the time for another couple of questions?
Of course.
We have just a few minutes. Marina, Francesca, and then I'll say 2 minutes for your last one.
In which respect this strategy of using the justice statements is different from a nominalistic way to paraphrase?
I've been thinking about this.
Yes. That is part 2 of the talk. So on this view, on the view that for the number of the dinosaurs to be 0, just as for there to be no numbers, it is strictly and literally true that numbers exist. In fact, on that view, it would be absurd for numbers not to exist. And I'm going to prove it to you. So, use a generalized version of this. So just say that for the number of the f's, for the number of the f's to the n, just is for there to be exactly n f's. So say that that's true in general. I'm going to assume this and prove to you that a world with no numbers would be absurd. Suppose for reductio that there are no numbers. But wait. For the number of the numbers to be 0, just is for there to be no numbers. So the number of the numbers is 0. So 0 exists. So there are numbers. Contradiction. In other words, if you accept this principle, you can derive a contradiction from the assumption that there are no numbers. I'm going to say the proof just once more, just because it's so beautiful and because it seems like there must be some mistake the first time around. Okay, so the proof presupposes this principle and derives a contradiction from the assumption that there are no numbers. Assume for a reductor that there are no numbers, but for the number of the numbers to be 0, just as for there to be no numbers. So the number of the numbers must be 0. And if the number of the numbers is 0, then 0 exists. And 0 is a number. So there are numbers, contradicting our assumption. So someone who, like me, accepts this principle is committed to thinking that on pain of contradiction, numbers exist. And that is the exact negation of, well, it's stronger than the negation of nominalism. Now, but there is something I share with nominalists, something important. Nominalists, or at least nominalists of the façon de parler variety, think that when you say something like the number of dinosaurs is 0, you're saying something quite innocent. You're saying something that, like, doesn't require God to have created like some weird metaphysical things. And with that, I agree. Except that they think it because they think that you're not really committed to numbers. I think it because I think that you are committed to numbers, but that commitment to numbers is no commitment at all. It's the kind of thing that can only fail to exist on pain of contradiction. So it's the kind of thing that God couldn't have but included in the world. In the same sort of way that God couldn't have but made it the case that either P or not P. So it's a consequence of my view that contra quine, ontological commitment, is not a good way of measuring how demanding the truth of a sentence is on the world.
Very good. Thanks for answering my question. And we have time for the last one. Francesca.
Got two questions, but okay. We can talk about this later, but I'm quite suspicious about what you just said. I've got questions about pluralities. I've got questions about second-order logic. Allowing nominalists to use second-order logic, it doesn't work, I think. But just this last bit. Well, paraphrase is a two-way street, right? So you can go from one sentence to another, and you have the converse translations, right? So what really matters to the nominalist is that the assumption of the existence of a paraphrasing function, you also have, you can sort out which direction you should go to by adding the requirement of less ontological commitment. So I'm not completely clear on your last argument, because it looks like it's against it uses the notion of paraphrase without the further assumption that the nominalist has to do in order to provide paraphrase with the right direction.
I'm glad you asked that. So that is a crucial respect in which I have departed from the nominalist project. Because as you point out, nominalists of the kind we've been discussing really do think there's a direction. So they really do think that you start with sentences which are very demanding, and you find paraphrases which are undemanding. But what I think is that the original sentences were already undemanding. So it's not that you need to move to a less demanding sentence. You were already there. Now, the result that I described in the talk has a consequence for my view. So, because it's impossible to specify a trivialist paraphrase function, one thing I cannot do is find for every arithmetical sentence a just this statement that plugs in a non-mathematical paraphrase there. That can't be done. I can't do it any more than the nominalists can do it. So the project isn't really a paraphrase project. What the project does is suggest, it's really this, it's a Fregean idea. What the project does is suggest that there is a certain fact, a certain feature of the world that can be, as it were, carved up in different ways. So there is a single feature of reality that might be described by saying there are no dinosaurs, or described by saying the number of the dinosaurs is 0. And you're really just talking about the same thing. It's just that in describing it using different sentences, you are structuring it in different ways. So it's really a view about which sentences describe the same facts and which ones do not. Now, there is a cool thing you can do, which is this. So think of this as my opening a parenthesis. If you don't understand, don't worry about it. Like, just think about something else. I'll close the parenthesis when the time comes. So you can't really give a paraphrase, but here is something you can. You can give a compositional semantics that assigns to each sentence in the language of arithmetic, or indeed the language of set theory, trivialist truth conditions. Now, the reason that doesn't contradict the paraphrase theory is that in your meta theory, the theory you use to give the semantics, you inevitably have to use mathematical vocabulary. So you use mathematical vocabulary to specify truth conditions, but the truth conditions thereby specified are nominalistic. So you use a mathematical method to specify non-mathematical truth conditions. So one thing you can do is you can